Hello, my name is Janine Stroop, and I'm a biochemistry major from the class of 2019.
My name is Nicole Canop, and I am a chemistry major from the class of 2019. We'll be working through problem number 2 from chapter 2.4, Practice Problems in the General Chemistry Workbook.
This problem deals with empirical formulas. An empirical formula is a way of expressing the ratio between the number of atoms of each individual element that makes up a compound. Unlike a molecular formula, the empirical formula does not directly tell us how many atoms of each element are in a molecule. It only tells us the simplified ratio between those atoms. For example, ethane, which looks like this, has an empirical formula of CH3, because as you can see here, there are 2 carbon atoms in this molecule and 6 hydrogen atoms. This gives ethane a molecular formula of C2H6. But since we write empirical formulas in the most simplified form, C2H6 becomes CH3. This tells us that ethane has 3 hydrogen atoms for every 1 carbon atom. Empirical formulas can be useful for determining a compound structure from mass percentages. This concept applies to Part A of question 2.4. Go ahead and pause the video and try to solve Part A on your own now. Okay, so in Part A, you're given the percent mass of carbon, oxygen, and hydrogen in a compound. First, we want to assume that the total mass of this sample is 100 grams, so that the mass of each element equals the percent given. So for Part A, when we assume a 100-gram sample, the 52.14% carbon becomes 52.14 grams of carbon. The same applies for the 34.73% oxygen and for the hydrogen. Now, in order to compare quantities of different elements to each other, we must first convert to moles. So we're going to convert the mass of each element to moles by dividing by the molar mass from the periodic table. So for carbon, we're going to divide by 12 grams per mole. And for oxygen, we'll divide by 16 grams per mole. And for hydrogen, we'll divide by 1 gram per mole. Okay, so this gives us 4.34 moles of carbon, 2.17 moles of oxygen, and 13.13 moles of hydrogen. So now we want to find the mole ratios between the elements by dividing the mole value of each element by the smallest number of moles calculated. This will give us the most simplified mole ratio of all the elements in the compound, which is essentially what an empirical formula is. So our smallest mole value is 2.17 moles of oxygen, so we're going to divide all of the mole values by 2.17. This gives us ratios of 2 moles of carbon for every 1 mole of oxygen, 1 mole of oxygen, and 6 moles of hydrogen for every 1 mole of oxygen. So we end up with an empirical formula of C2H6O. Part B follows essentially the same process as Part A. Go ahead and pause the video and try Part B on your own now. Okay, so here's our work for Part B. Essentially the same process. We assumed a 100-gram sample, so that turned all of the grams, all the percentages into grams, and then we converted from grams to moles using molar mass, and then we divided by our smallest mole number to get our mole ratios. Now here's where Part B gets a little bit different from Part A. For our ratio of carbon to oxygen, we end up with 1.5. Now an empirical formula can only have whole number subscripts, so to fix this problem, we're going to multiply all of our mole ratios by 2, giving us 3, 2, and 8. And now we can write our empirical formula with whole number subscripts. So that'll be C3H8O2. Part C is a little different. So in Part C, we're talking about the combustion of a hydrocarbon. The combustion of any hydrocarbon follows this chemical equation. CxHyOZ plus O2 yields H2O plus carbon dioxide, where X, Y, and Z represent the numbers of atoms of carbon, hydrogen, and oxygen in one CxHyOZ molecule. In order to find the empirical formula for this hydrocarbon, we must determine X, Y, and Z. Let's think about the products formed, carbon dioxide and water. The oxygen in these molecules could have come from either reactant, but we know that all of the carbon in carbon dioxide and all of the hydrogen in water must have come from the hydrocarbon and not the O2. We also know that the hydrocarbon is reacting with excess oxygen, so it is acting as a limiting reagent. This means that all 60.68 grams of the hydrocarbon will be converted into products in this reaction. So, if we can find how many grams of carbon are in 89.12 grams of carbon dioxide, then we know we started with that same number of grams of carbon in CxHyOZ. To do this, we convert 89.12 grams to moles by dividing by the molecular weight of carbon dioxide, which is 44 grams per mole. Then we use a 1-to-1 mole ratio to convert moles of carbon dioxide to moles of carbon, because the subscripts in CO2 tell us that there is 1 mole of carbon for every 1 mole of carbon dioxide. Now that we have moles of carbon, we can convert this back to grams by multiplying by the molar mass of carbon. This gives us 24.3 grams of carbon. Now we can divide the 24.3 by 60.68 and multiply by 100 to find what percent of the total mass of the sample carbon makes up. This gives us 40%. So the same concept can be applied to hydrogen. So we will convert grams of water to moles by dividing by the molar mass of water. And then we'll use a 2-to-1 mole ratio to convert moles of water to moles of hydrogen, because there's 2 moles of hydrogen in every 1 mole of water. And then we'll use the mass of hydrogen to convert 2 grams of hydrogen. So this gives us 4.053 grams of hydrogen. Now when we divide by 60.68 and multiply by 100 to get our percent mass, we end up with 6.68% hydrogen. Okay, so now we can find our percent of oxygen by subtracting. We know that the percents have to add up to 100, so we can just subtract the sum of the percent of carbon and the percent of hydrogen from 100. And that gives us 54% oxygen. Okay, from here we can solve this problem the same way we solved problems A and B, because we have the percent mass of each element in the hydrocarbon now. So we can assume a 100-gram sample like before, and this allows us to convert the percents into masses. So we have 40 grams of carbon in our 100-gram sample, and then we're going to convert that to moles by dividing by the molar mass. and that gives us 3.33 moles of carbon. So we can do the same thing for our hydrogen now. If we have 6.68 grams of hydrogen and we divide by the molar mass of 1 gram per mole, we're going to get 6.68 moles of hydrogen. And same goes for oxygen. Our 54 grams of oxygen gets divided by 16 grams per mole, and we end up with 3.4 moles of oxygen. So now, like before, we're going to find our mole ratios by dividing by our smallest mole value, which is 3.33. And now we end up with 1 mole of carbon, 2 moles of hydrogen, and 1 mole of oxygen. This gives us an empirical formula of CH2O. Okay, so here's our work for part D. Again, we assumed a 100-gram sample and converted the percents to masses, and then we converted the mass to moles using molar mass. So we had 6.3 moles of carbon, 0.969 moles of oxygen, and 8.8 moles of hydrogen. Then we divided by the smallest amount of moles to get our mole ratios. So we got 6.5 moles of carbon, 1 mole of oxygen, and 9.02 moles of hydrogen. Since we had 6.5 moles, to get to whole number ratios, we multiplied everything by 2, giving us 13 moles of carbon, 2 moles of oxygen, and 18 moles of hydrogen. Our overall empirical formula was then C13H18O2. Okay, so here's our work for E, so that you can check it with yours. It's essentially the exact same process as the previous parts. Okay, and here's the work for F. So again, the same process, just with different elements. And when you're writing your empirical formula, you're going to want to put the ZR in front because it's your metal, and then you can put silicon and oxygen after that. So we end up with ZrSiO4.